friends, in the previous lecture we have discussed regarding the half cycle DFT, and in that we have seen that the phasor value that is to be estimated for any harmonic component or fundamental or DC term that is given by the equation capital C into sigma n is equal to 0 to n by 2 minus 1 x of n e raised to minus j 2 pi by n k n, where C is 1 divided by n by 2 for DC and it is 2 divided by n by 2 for sinusoidal components. After that we have also discussed one example of half cycle DFT, and in that example we have seen that whatever phase number of samples we considered, which is practically half the value of full cycle DFT, then also the phasor value that is to be estimated are almost equal to the same value estimated by full cycle DFT. After that we have discussed the comparison of full cycle DFT and half cycle DFT. So, in this comparison we have done based on three important parameters. So, the first parameter is the accuracy, and we have discussed that as the number of samples required per window in case of full cycle DFT, that is higher than the number of samples required in half cycle DFT. So, accuracy of full cycle DFT is better compared to the half cycle DFT. Then we have considered another parameter for the comparison of performance of full cycle DFT and half cycle DFT, that is computational complexity. So, as the number of samples required in full cycle DFT is higher compared to half cycle DFT, so computational requirement reduces if we use or if we go for half cycle DFT for phasor estimation. So, this is also another important parameter. So, that is computational complexity. And the third thing is the rejection of harmonics. So, this is also an important parameter for comparison. So, we have discussed that if we consider the full cycle DFT, then this algorithm is capable to reject both even as well as odd harmonics, whereas half cycle DFT is not capable to reject even harmonics. So, this we have discussed. After that we have discussed the limitation of DFT, whether full cycle or half cycle, and we have discussed that if decaying DC component is involved in the acquired signal, and this is the case when fault occurs. So, when we acquire the samples from fault current signal, then decaying DC component is present. So, in that case the DFT is not capable to accurately estimate the phasor values. After that we have discussed another algorithm, that is cosine transform, and in this transform we have discussed that the sine component we can replace with the cosine term. So, the sample calculations required for cosine transform that can be reduced. However, the unavoidable time delay is included when we use cosine transform. So, it requires n plus n by 4 samples compared to the DFT, which requires n samples. And after that we have discussed the application perspective of cosine transform, and that we have discussed that cosine transform compared to the DFT, whether full cycle or half cycle, how effective we can utilize the cosine transform algorithm for phasor estimation of the signals. Now, in today's class let us extend our discussion and let us discuss about the recursive DFT. So, recursive DFT is an extension of our conventional full cycle DFT, and in this DFT an observer based computational algorithm is used to acquire the components or the samples from the signals. So, in this algorithm the recalculation of sine and cosine filter values for every new incoming samples in a particular window that is to be carried out. So, if we consider here, you can see there are two windows, this is the first window and this is the second window. So, when in the first window you know that the samples from I1 to I8 are available, and when you use these 8 samples in window 1, then you can easily estimate the phasor value. So, phasor value of window 1 is already available, and now when you move from first window to the second window, the only change is that the first sample, that is I1, that is discarded, and the new sample I9 that is to be included. So, for window 1, sample number varies from I1 to I8, whereas for window 2 the sample number varies from I2 to I9. So, the only change that is going to occur in window 2, that is the sample number I9 and sample number I1. So, this clearly indicates that there is no need of calculation of samples I2 to I8, because that we have already done in the first window or the previous window. So, to understand the recursive DFT for any, let us say, fundamental phasor, so assuming k is equal to 1, mathematically we can represent the recursive DFT as x of r plus 1, that is equal to x of r plus c into x of n plus r minus x of r, and that is multiplied with e raised to minus j 2 pi by n. Now, here r is nothing but the window, a particular window. So, here you can see the two windows I have shown. This window is your rth window and the next window, that is your r plus 1th window. And as I told you, as I explained earlier, that when you move from first window or rth window to the r plus 1th window, then only the two samples, that is I1 and I9, you need to consider. The remaining samples are same with reference to the previous rth window. Here you can see that n is the number of samples in a cycle. So, that is also here in this case, this samples are 8 in this case. So, if I consider in this case, let us say for example, let us calculate the phasor value of fundamental component of this signal IT, which is given by some DC value, let us say 2, with some fundamental component, let us say 10 angle 0, some third harmonic term, let us say 3 angle pi by 4, and the fifth harmonic term, that is let us say 1 angle pi by 2 or 1 angle 90 degree. Here this signal, when we acquire the samples, the fundamental frequency is 50 hertz and the sampling frequency is 800 hertz. Whatever value we acquired for respective samples are given in this table. So, you can see that sample number 1 to sample number 24 are given, and for each sample the acquired value, that is also listed in the table. Now, using this, if we calculate the phasor value of the first window. So, here as the sampling frequency Fs is 800 hertz and fundamental frequency F0 is 50 hertz. So, your number of samples in a cycle, that is 16 Fs by F0. So, if you consider the first window, let us say from sample number 1 to sample number 16, and if you calculate using this 16 samples in a window or in a cycle, the phasor value, let us say that value is given by x1, and that value you can obtain, that is 10 angle 0, and this is for fundamental component. So, here you can see that for this first 16 samples, the phasor value of the fundamental component comes out to be 10 angle 0. Now, when you move to the next window, right, that is the second window, let us say the second window is from 2 to 17. So, your first window, that is from let us say 1 to 16 samples, and your second window, that is from let us say 2 to 17 samples. So, the only difference that is for sample number 1, that is that needs to be discarded, and sample number 17 that is to be included. So, we have already calculated the phasor value x 1 for fundamental component, that is tan angle 0 for first window when we considered 1 to 16 samples. Now, when you want to calculate the phasor value for second window, which contains sample number 2 to sample number 17, then using this equation x of r plus 1 is equal to x r, if I use this equation, then you can see that the value comes out to be this. So, here let us consider r that is equal to 1. So, when I consider r is equal to 1, this value, that is x of r plus 1. So, x of 2 for which second window we want to calculate the phasor value, that is x of r. So, r is 1. So, this is x 1. So, x 1 we have already calculated the value, that is tan angle 0, the c that is 2 by n, and x of n plus r. So, n is 16 and r is 1. So, this is x 17, that is 14.1 value, and minus x of r. So, this is x of 1. So, that is 14.1 again. So, when you calculate the phasor value for second window x 2, so that comes out to be tan angle 0 and this value is 0. So, tan angle 0 plus 0 e to the power minus j 2 pi by n. So, this value comes out to be x 2, that is magnitude remains same 10, the only change that is in angle, that is 22.5 degree. Now, if we further proceed, let us say third window, that is from let us say sample number 3 to sample number 18. So, when we consider the third window and if we calculate the value of x 3, then the equation is x 2, because this becomes now x 1 becomes x 2, 2 by n, and this value that is already mentioned. So, now we have the value of x 3 comes out to be tan angle 45 degree. So, you can see that when you take a new window, then the only difference that comes out to be here, that is in the phase angle. So, we can say that when we use the recursive DFT, computational requirement reduces, because when you move from one window to other window, you have to consider only those samples which are available. So, new sample as well as the sample which needs to be discarded. Moreover, as this method is similar to DFT, so it also faces a problem of the inability of computation of phasor when decaying DC component is present in the signal. So, when fault occurs, fault signals normally contains decaying DC component. So, when such component is there and when you acquire the sample for estimation of phasor value, then recursive DFT is also not able to accurately estimate the phasor value. Now, let us move to the next phasor estimation algorithm, which is known as least square estimation or LES algorithm. So, this LES technique reduces the mean square error value between the assumed value and the original values. So, when we consider DFT, that is discrete Fourier transform algorithm, and when we acquired samples of either voltage or current signals for the estimation of let us say DC term or fundamental term or any other higher order harmonics, then in that case when decaying DC component is present in the acquired signal, especially in case of fault, LES technique performs better. We will see how it performs better. So, when decaying DC component is present, then instead of utilizing DFT or cosine transform or any other recursive DFT or any other extended version of DFT algorithm, we must go for the LES technique. Now, let us see how the LES technique works. So, let us consider a current signal IT, which is given by IT is equal to this equation. So, this equation of current, it has a term I 0, that is a DC component, it has a fundamental term I 1, it has a third harmonic term, that is this one I 3 cos 3 omega 0 t plus theta 3, and it also has a fifth harmonic component, that is I 5 cos 5 omega 0 t plus theta 5. So, here you can see that this I t is nothing but the instantaneous value of current which changes with reference to time. The I 0, I 1, I 3 and I 5, these are the magnitudes of DC component, fundamental, third and fifth harmonics respectively. If I consider the theta 1, theta 3 and theta 5, then these are the phase angles of fundamental, third and fifth harmonics respectively, and omega 0 is nothing but the fundamental angular frequency of the current signal, that is I t, for which we are going to acquire the samples. Now, if I use the trigonometric identities, then we know that the equation of cos of alpha plus beta, that is given by cos alpha cos beta minus sin alpha sin beta. So, if I use this cos alpha cos beta minus sin alpha sin beta, if I use this, then we can say that the earlier equation, in this equation the term I 1 cos of omega 0 t plus theta 1. So, we can extend this cos of omega 0 t plus theta 1 in terms of cos of alpha plus beta. So, where alpha is omega 0 t and beta is theta 1. So, if I extend using this, then we have I t, that is the DC term I 0 plus I 1 cos theta 1 into cos omega 0 t minus I 1 sin theta 1 into sin omega 0 t. Similarly, if I again extend this term and this term with reference to cos of alpha plus beta, this equation, then we can have I 3 cos theta 3 into cos of 3 omega 0 t minus I 3 sin theta 3 into sin 3 omega 0 t. Same way you have I 5 cos theta 5 into cos 5 omega 0 t minus I 5 sin theta 5 into sin 5 omega 0 t. Now, here in this equation, if I substitute t, that is equal to n t s, where n is the sample number which varies for a particular window. If I have, let us say 16 samples in a window, then n varies from 1 to 16, like that. And if this T s is nothing but your sampling time, which is nothing but the reciprocal of sampling frequency, that is 1 upon f s. So, if I replace t equal to n T s in this equation, then we have the value of I t, that is given by I 0 into I 1 cos theta 1, that is same cos omega 0 t I am replacing with n T s. Same way here also, instead of t I am putting n T s, and here also we are replacing the same t with n into T s. So, we have this equation. Now, this equation, if I write down in the matrix form this equation, then we have the term, that is this I 1 cos theta 1, we have the term I 1 sin theta 1, we have the term I 3 cos theta 3, and we have the term I 3 sin theta 3. Similarly, we have I 5 cos theta 5 and we have I 5 sin theta 5 and we have the I 0 term. So, if I put this term, that is I 0, I 1 cos theta 1, similarly I 1 sin theta 1, I 3 cos theta 3 and I 3 sin theta 3, and similarly I 5 cos theta 5 and sin theta 5. So, these are the unknown values, and on right hand side the known values, that is nothing but the samples which we are acquiring for this current signal. So, that sample varies from I 1 to let us say I p, where p is nothing but the consecutive samples. So, that value of p that is variable, in that case n varies from 1 to p. So, if I have let us say 16 samples, then this small n varies from 1 to 16. So, in this equation, if I replace this or rewrite in terms of matrix form, then we have the term, you can see here I 0 is there. So, if I take I 0 on unknown side, so and this becomes 1. So, we have the 1, then we have the term, that is this term, that you have here cos omega 0 n we are putting as, let us say, sample number 1. So, here we have cos omega 0 n is 1 into T s. Similarly, we have here sin omega 0 n is 1 into T s. So, we have this term cos omega 0 T s here. Similarly, we have sin omega 0 T s with negative sign. So, we have this term, that is sin omega 0 T s. Same way, if you write down cos 3 omega 0 n is 1 into T s and sin 3 omega 0 n into T s. So, you have the term this one and this one, and similarly you have this term. Now, this is for n is equal to 1. So, if you again put n is equal to 2, then you have 1 cos omega 0 2 T s, again sin term, again this term. So, similarly, if you extend, you will have the last row in which you have this elements, that is cos omega 0 p T s minus sin omega 0 p T s and so on. So, this matrix, which is nothing but p cross 7. The 7 number we will explain, because we have the 7 unknowns, that is why this 7 number comes here. And on right hand side we have this samples which are known, that varies from I1 to IP. So, size of this matrix is p cross 1. So, if I called this matrix as A, if I called unknown as matrix X, and if I call known value of samples, that is matrix B, then the size of B is p cross 1, the size of X, that is 7 cross 1, because we have 7 unknowns, and size of A, that is again p cross 7. So, here you can see that the unknown values are I 0 and I 1 cos theta 1 sin theta 1, similarly I 3 cos theta 3 and sin theta 3, and we have I 5 cos theta 5 and I 5 sin theta 5. So, total unknowns we have, that is 7. So, for any equations, if we want to estimate the unknowns, then the thumb rule is that we need minimum that much samples for the minimum unknown values. So, here unknown values are 7. So, we need at least 7 samples. So, here this samples varies from I 1 to up to 7 values. So, 7 samples I 1 to I 7 we required, or maybe we have higher samples, that is also okay, but minimum 7 samples are needed. So, in general form, if I write this equation, that is A into X, that is equal to B, this matrix, then I can write A, which size is p cross 7. So, 7 I am replacing with the term 2h plus 1, where h is nothing but the total harmonics present in the signal. So, here you can see in the earlier signal we have the harmonics DC value, and the other harmonics are fundamental, third and fifth, right, 2 values for each. So, 2 into 3 6 plus I 0, that is 7. So, that is why this 2h plus 1. So, 1 indicates the DC value, h indicates the harmonics. So, this is how the size of A matrix is available. Similarly, the size of X matrix you can see here, that is unknowns, that is 7 cross 1. So, 7 I am replacing again with 2h plus 1, and same way we have the B matrix, that is p cross 1. Now, in this above equation you can see that for accurate measurement of phasors of all the harmonics present in the acquired signal, so minimum we need 2h plus 1 sample. So, as I told you, we need at least 7 samples if 7 unknowns are there. That is why the solution of for matrix X, we need P, that is the number of samples, which is always greater than or equal to 2h plus 1. If it is less than, then we are not able to calculate the or find out the unknown values. Now, let us discuss practicality of LES technique. So, in actual practice, we know that whenever we acquire the samples, then your signals may contain some errors like measurement errors or observational errors. So, in such a situation, if I use LES algorithm for estimation of phasors, then this is the best technique. How? So, when the considered equations, let us say samples P available are more than the unknowns. So, when the value of P is greater than 2h plus 1, right. Minimum is p is equal to 2h plus 1, but if the samples are more than the unknowns, then in that case LES algorithm performs better compared to the earlier algorithms. Now, let us discuss one important point. When we consider the matrix A and when the number of samples available that is same as 2h plus 1. So, if we have 7 unknowns and if 7 samples are available, then the size of this matrix A, that is a square matrix, and we can easily find out the inverse. But when we have the value of number of samples available that is greater than the 2h plus 1, that is more than the unknown values, then the size of the matrix A, that becomes a non-square matrix, and inverse of this matrix is possible by pseudo inverse technique. So, here if I consider pseudo inverse of A matrix, let us say A plus, that is nothing but A transpose into A whole inverse multiplied by A transpose. So, if I write down this value, that is pseudo inverse A plus, here same equation, then we can say that A transpose size is 2h plus 1 into p. This we have already discussed earlier. So, the size of A, that is p into 2h plus 1. So, size of A transpose, that is reverse 2h plus 1 into p. So, that is here available. Again A, that is p into 2h plus 1 and whole inverse into A transpose, that is this value. So, if you combine these two, then you can have, you see the size, that is 2h plus 1 into 2h plus 1. So, your matrix becomes square and then you have the A transpose. So, finally, the pseudo inverse of A, that is A plus, it has the size that is 2h plus 1 into p, which is given by this thing. As I told you, size of the A pseudo inverse of A, that is 2h plus 1 into p. So, this is really important equation which we need to remember. Now, if I use this pseudo inverse of A, then the unknown value of x, that can be easily calculated, and size of this pseudo inverse of A, that is 2h plus 1 into p, and size of B is p cross 1. So, we have the unknown matrix X, its size is 2h plus 1 into 1. Now, the important point is the elements of this matrix A depends on two parameters. One is the TS sampling period and another is the sample numbers, and these values are constant. So, whenever we consider or when we calculate the pseudo inverse of matrix A, we have to calculate this matrix once only. There is no need to calculate this matrix again and again for each and every iteration. So, our final equation of unknown value of x, that is given by this equation, and its size is 2h plus 1 cross 1. So, this will give you the value of x which is unknown. So, we have DC value, we have I1 cos theta 1, I1 sin theta 1, I3 cos theta 3, I3 sin theta 3, I5 cos theta 5 and I5 sin theta 5. So, here you can see that when you consider the value of this x unknown, size of which is 2s plus 1 cross 1. So, in that case, if we wish to calculate the phasor value, then phasor is normally represented by AM angle theta. So, here you can see that if I want to calculate, let us say phasor of this, then AM cos theta is nothing but your I1 cos theta 1 and your I1 sin theta 1 is nothing but your AM sin theta. So, I1 cos theta 1 plus j I1 sin theta 1, that is nothing but the phasor value of this term, right. Similarly, you can calculate the phasor value of third and fifth harmonic, so that you can easily calculate. So, here you can see that in this first row represents the DC value, whereas the real and imaginary part of other harmonic components that can be achieved when you obtain the value of x. So, in this class we have discussed initially what is the equation of recursive DFT algorithm, and we have discussed that when we want to use recursive DFT, then there is no need of calculation of several samples except the new sample and the discarded sample. So, we can tremendously reduce the computational requirement when we use recursive DFT. We have also discussed one example of recursive DFT, and thereafter we have discussed the new Phasor estimation algorithm, that is LES technique. We have discussed that how mathematically LES can be represented and how we can obtain the Phasor value of LES technique when the number of unknown or samples are greater than or equal to the unknown values, that is 2h plus 1. Thank you.